Today we are going to discuss mutually induced EMF, mutual inductance and eddy currents. Let's start with mutually induced EMF. The EMF induced in a coil due to the change of current in a neighboring coil is called mutually induced EMF. So this EMF is induced in one coil due to the change in current in another coil. In order to demonstrate the phenomena of mutually induced EMF, let us place two coils A and B adjacent to each other. Now this coil A and this coil B are placed adjacent to each other. When the current flows in coil A, then there will be magnetic field produced around it. We know that when current is flowing through this coil A, then there will be magnetic field around this coil. A part of the magnetic flux produced by coil A passes through or links with coil B. This current in this coil is producing magnetic field around this coil, and flux produced in this coil is also passing through this coil. This flux, which is common to both the coils A and B, is called mutual flux. Now flux flowing through this coil is also flowing through this coil, so it is called as mutual flux because this flux is common in both the coils. If current in coil A is varied, the mutual flux also varies and hence EMF is induced in both the coils. We know that whenever current changes in a coil and due to current changes, magnetic flux also changes through the coil, and due to change in flux there will be induced EMF. So here we have change in current in coil A, and due to change in current coil A, magnetic flux through both the coils, that is mutual flux, is also changing. Due to change in mutual flux there will be induced EMF in both the coils. The EMF induced in coil A is called self-induced EMF. The EMF induced in coil B is called mutually induced EMF because EMF induced in coil B is due to change in current in coil A. So that's why induced EMF in coil B is known as mutually induced EMF. The mutually induced EMF in coil B persists so long as the current in coil A is changing. We know that the change in current in coil A is cause of induced EMF in coil B, that is mutually induced EMF in coil B. So when current is constant or current is not changing in coil A, so there will be no mutually induced EMF in coil B. The magnitude of mutually induced EMF is given by Faraday's law, that is EMF is equals to NB, that is number of turns of coil B, delta phi m divided by delta T, that is rate of change of flux. Mutual inductance. According to Faraday's law of electromagnetic induction, induced EMF in a coil depends upon the number of turns and rate of change of magnetic flux linking the coil. Mutually induced EMF in coil B is directly proportional to rate of change of current in coil A, and we know this thing that due to rate of change of current in coil A, mutually induced EMF is produced in coil B. Mutually induced EMF is directly proportional to rate of change of current in coil A. So EMF, mutually induced EMF, is directly proportional to delta I divided by delta T, rate of change of current in coil A, and here constant is M. M is mutual inductance, and we get mutually induced EMF is equals to delta Mi divided by delta T. Mutual inductance occurs when two coils are placed together. As we have discussed, two coils, coil A and coil B, are placed together, and magnetic flux that is through coil A is also passing through coil B. So magnetic flux is linked with both the coils, and we call this as both coils are coupled. Each coil has own inductance, but there is further inductance due to the induced voltage produced by coupling between the coils, and that is known as mutual inductance. And the two coils are coupled together by mutual inductance. That further inductance is known as mutual inductance. Because both coils are coupled together, and due to the coupling of coils there is induced voltage, and due to that we have further inductance, and that inductance is known as mutual inductance. Let's say equation number 1. If EMF is equals to 1 volt and rate of change of current delta I divided by delta T is equals to 1, then we have mutual inductance equals to 1 Henry. So mutual inductance between two coils is 1 Henry if current changing at the rate of 1 ampere per second in one coil induces an EMF of 1 volt in the other coil, where M is a constant called mutual inductance between two coils. The unit of mutual inductance is Henry. Since as we know that EMF is equals to N delta phi divided by delta T, let's say it equation number 2. Comparing equation number 1 and equation number 2, we have Mi is equals to N phi. And from here we can get M is equals to N phi divided by I. So mutual inductance is equals to N number of turns of coil, phi flux divided by I current. Eddy currents. Eddy currents are currents induced in metals moving in a magnetic field, or metals that are exposed to a changing magnetic field. So when a conductor is moving in a magnetic field, so flux will be changed through that conductor, and the current induced is known as eddy currents in that conductor. Or if metal are exposed to a changing magnetic field, when magnetic field is changing and metal is placed near that changing magnetic field, then flux through that conductor or metal will be changed, and due to that induced current will be produced, and that induced current is known as eddy currents. Consider a solid metallic cylinder rotating in a B field magnetic field as shown in figure. A force resisting the rotation would be generated as shown. Heat would be generated by the induced current in cylinder. When a solid cylinder is moving in a magnetic field, solid cylinder is rotating in a magnetic field, so a resisting force will be produced which will resist the rotation of the cylinder, metallic cylinder, and heat will be generated due to induced current in the cylinder. To reduce eddy currents, the solid cylinder could be replaced with a stack of coins with insulation between one another. So we can reduce this heating effect, and we can reduce this eddy current by using a stack of coins instead of solid cylinder, and we can insulate that stacks of coins with each another to avoid eddy currents. The insulation between the coins increases resistance and reduces eddy currents, thus reducing friction or heating. So by using insulation between the stack of coins, we can increase the resistance, and due to that eddy currents will be reduced and there will be low friction and heating effect will be reduced. Here is a solid metallic conductor, and this conductor is moving in a magnetic field B due to the rotation of this solid cylinder, metallic solid cylinder. Flux is changing through this metallic cylinder or conductor. So due to change in flux, there is induced current, and that induced current is known as eddy current because it is swirling in this conductor, such as swirling of water, swirling of stored water. So that's why it is known as eddy current, because it has no path to flow, it is just rotating within this conductor. And there is applied force which is resisting the rotation of this conductor. And due to this eddy current, heat is generated in this conductor. To avoid heating effect, we can use stack of coins, and these coins are insulated with one another so that we can reduce the heating effect. Here we have another way of generating eddy currents or demonstrating eddy currents. Here we have a conductor, and that is not rotating. It is a static conductor. And we have a coil, and it is connected with AC supply. Due to AC supply, there is change in current through this coil, and that change in current is changing the electromagnetic field or flux, and this flux is changing. So due to this change in flux, eddy current is generated in this conductor because this flux is passing through this conductor, and this flux is changing continuously. Due to change in this flux through this conductor, there will be eddy currents produced in this conductor. This animation is also showing the same procedure. Here magnetic field is changing. We have a magnet and we place or move it towards this conductor. When we move this magnet towards this metallic plate, we can see that due to change in magnetic flux through this metallic plate, eddy currents is produced. Eddy currents application. Here we have a coil and current is flowing through this coil. Due to flow of current, we know that there must be a magnetic field around this coil. And we have a coin near to this coil. Flux produced through this coil is also passing through this coin. Now we are applying a pulsing current, and that is changing current. Due to change in current, magnetic flux must be changing through this coil. So it will also be changed through this coin. So there is changing magnetic field through this coil and through this coin. Due to the change in magnetic flux through this coin, there will be eddy current in this coin. And this is used in metal detectors. A pulsing current is applied to the coil, which then induces a magnetic field shown. When the magnetic field of the coil moves across metal such as the coin in this illustration, the field induces electric currents called eddy currents in the coin. The eddy currents induce their own magnetic field, which generates an opposite current in the coil, which induces a signal indicating the presence of metal. We know that due to the change in magnetic flux through this coil, there must be induced current, and that is known as eddy current because it will be within the conductor, it will be rotating within the coin. Due to the eddy current, there must be magnetic field due to the eddy currents because eddy currents induce their own magnetic field, and the magnetic field of eddy currents will generate opposite current in the coil, and that will indicate a signal, or that will induce a signal indicating that a presence of metal. So by this procedure we can detect metals, and this is the phenomena or procedure of metal detectors.